Welcome to our work report for the Parallax Education Day. I am Jesús.
And this is Evren.
And let's go on.
In our first assignment from Aalto University, we have used performance simulation environment toolset for evaluating how a system behaves when different hardware is used within. We have started by using a simple model, and then we have modified the model and re-evaluated the performance step by step. In this assignment, we had two tasks. The first task was adding a special accelerator device, and then evaluate the impact of this device on the system performance. The second task was upgrading the memory system by adding L2 cache, and then evaluate the impact of the L2 cache on the RAM utilization. In the first task, we have modified the basic block B in the software model for adding the accelerator. Adding the accelerator required releasing the CPU and requiring the CPU in between. Here we can see the accelerator in the hardware model. We have added the necessary probes for evaluating its effects on the performance. In this graph, we can see the utilization of active CPUs before and after adding the accelerator. The accelerator is shown in green color in the second graph. We have modified the output script so that we can see the accelerator separately in the graphs. As can be seen clearly, the accelerator have reduced the usage of CPU cores significantly. Here we can see the queue lengths before and after adding the accelerator. The addition of the accelerator slightly reduced the queue length of the processor. Again, the accelerator can be seen in green color in the after graph. Here we see the memory models after adding the L2 cache, both for reading and writing. As can be seen clearly, we had to check the memory hierarchy when writing and reading data for existing data. In this slide, the L2 cache is seen in the hardware model, and of course it has the necessary probes for checking the performance of it. Here we see the graphs for before adding the L2 cache and after adding it. As can be seen clearly, the queue length has significantly been reduced after adding the L2 cache. Here we can see the usage of RAM channels before and after adding the L2 cache. As can be seen clearly, the L2 cache have reduced the usage of RAM channels significantly. In this exercise, we have learned how the addition of an accelerator and L2 cache affects the performance of a hardware system. In assignment 2 from Tampere University, we have used transport-triggered architecture for designing an abstract processor. In this assignment, we used the TTA-based code design environment TCE toolset for designing and programming a customized processor for Mandelbrot code. In this task, we have designed a processor based in the TTA architecture that fulfills three specific requirements. The requirements were so that the processor should use at most 65 instruction bits, and also there shouldn't be more than 16 connections per bus, and runtime should be less than 450,000 cycles. For designing this processor, we have profiled the program first, and then redesigned it and profiled it again, and kept on doing the same steps until we achieved our goal. Here is the profiling output from the original large processor with 4 buses. As can be seen, the arithmetic units are used quite often. Here is our final processor design. It uses 62 instruction bits and 15 connections per bus, and it is able to process the Mandelbrot in 449,859 cycles. Based on the initial profiling results, we have added an additional arithmetic unit to the processor. We have reduced the number of bus connections in these units, however, tried to make it so that the units can still function simultaneously. This resulted in our final design, which is functional within the specifications required by the assignment.
Hello, it is Jesús again. Now we move for the assignment number 3 from Oulu University, and it is about the CAL actor language. CAL is a high-level language for designing parallel systems under the data flow model of computation. In CAL, we design actors that will somehow model a process of computation that is applied to a flow of input data in order to obtain a flow of output data. For this assignment, we model a Sobel filter using this CAL language. Before moving into the Sobel filter, we had to answer 2 theoretical questions. We won't enter in detail here because we are supposed to send this theoretical task by email. With regard to the Sobel filter, there were 5 small subtasks within it. Here we have the answers to the theoretical questions, but we don't really need to look into them, so move on. For the first part of the Sobel application, we added a threshold to filter out values below 190. Just this simple code in the left is able to detect the edges of normal images. However, when it comes to process noisy images, like the upper one in this slide, the results are still noisy. In order to solve this problem, we had to add a 5x5 Gaussian filter. Now, when processing an input picture, we first apply the Gaussian filter and then the Sobel filter. That way, the resulting output should be free of noise. Once the Gauss and Sobel filter were finished, we had to ensure that our application was working properly. For that, we used MATLAB. When comparing our result to a given reference picture, in the left, we were supposed to obtain a PSNR higher than 30. However, we didn't. And you can see in the right image how there are some spots flying around the bird. After making sure that our application was working properly, and in our case it wasn't, we had to simulate how many cycles would it take for a DTA processor. The limit is 33 megacycles, however we don't know how many cycles take our implementation because it's still running after 8 hours. I think we will upload the result when we know them. To finish with this third assignment, here in the top is our final design. See how the flow first processes the input image with the Gaussian kernel and then applies the Sobel filter to obtain the edges in the picture. We believe that our design could be improved. That's why we added a second design in the bottom of this slide. The trick here is that sometimes 2-dimensional convolutions can be expressed as twice a 1-dimensional convolution. In this case, it is possible for both the Gaussian and the Sobel filters, and quite many operations would be saved. That's why we would recommend to implement this second version for an embedded processor or any very slow processor. And finally, the assignment from our university, Åbo Akademi, which consists in using the Silk language. Well, I have to say that Silk is not actually a language, but an extension to C++. Silk mainly allows you to easily express tasks and data parallelism. In the heart of Silk, you find a carefully designed, low-overhead scheduler. This scheduler spawns threads according to the till keywords that the user writes. Then it uses some job-stealing strategies to keep all cores in your CPU working at the maximum capacity. Our task was to parallelize an image matcher based on the paper, an image signature for any kind of image. The algorithm presented in this paper is able to match pictures of any size, and this is represented by the figure on bottom of this slide. With regard to the assignment, we had to parallelize at least one section and then run SilView to check whether the scalability was good or not. Because this assignment is from our university, we were good students and we didn't parallelize just one section, but 8. We won't go through the code because it would take too much time, but we would like to name at least the different parallelizations within. First, in a section of the code, the images are converted from color to grain. Here you can parallelize by pixel grain. Second, the pictures are divided into squares, and for each of those squares, the mean is computed. We parallelize this section so that each square is done in parallel. Third, the mean on the previous squares has to be done with an arithmetic reduction, but this reduction can be done in parallel as well. Fourth, when doing the previous mean, each pixel first smooths its value with the immediate neighbors. This is again another kind of arithmetic mean and can be reduced in parallel. Fifth, the application processes the absolute difference between each square and its neighbors. We do this in parallel square by square. Sixth, there is some more parallelism in this absolute difference related to the neighbors that they all are used, and this operation is also independent. 7. When thresholding the resulting signature, each element are independent, and this means more parallelism again. And 8. And last, parallelization when facing the signature of two images. This comparison is element by element, and since they are independent, this means parallelism one last time. And here we have the results from the SILView program, and you can observe in the left the whole program statistics. This means when we parallelize some sections, was the reduction in the time, taking everything into account, not only the parallel code but also the sequential. And you can see how for two processors it has like a good speed up, but once you go on and add more processor, it doesn't really scale because there is so few parallelism. However, in the right, the SILView program only takes into account the parallel regions, and you can see how the speed ups on the bottom are pretty good. For example, for 4 processor we have 3.8, but for 64 we have 60, what is a lot, and even for 256 we have 237, what is a crazy speed up. And this is the end. What can we say? Thank you very much for watching, and this was Jesús Evren from Åbo Akademi.